okay?
Yes, sir.
So this will be the polarity. The potential difference, this is V, this is circuit. Okay, let's see that the current, the direction of current will be same. Now this arrow, I'll change it here. In what action electrostatic force will be acted on this? Please say every numerical you must draw diagram like this. Not photons, everything. At least that E bar you have to show it because there is a concept. And now why E bar I'm changing? Because now the emitter is made. So I'll remove this cathode. So this is something like very difficult for you. Collector, emitter, finish short. Light is incident on a metal, that is emitter. The one which will collect photon, that is the collector. Now look at this. The positive terminal connected to emitter. Light is incident. Again, the same condition. So this is the intensity of the source I. Quantum efficiency of this, I'll write nearby it. What is the quantum efficiency? The efficiency of that particular metal. And the energy of photon is this much. The number of photons emitted by the source per second. Power of source by energy of photon. Clear this. These are number of photons emitted by source per second. Then how many photoelectrons are ejected? Will be eta into this. So then, so how much it will become? Eta PS lambda by SC. Will I agree this? Like I just bringing. Then what about current? Current should be equal to saturation current will be equal to some of you are asking. I just gave the giving this. So like this is what it is being derived. Fine. Now let's come to the discussion here. We are checking for the graph. No, what will happen to the graph? I'll put back the graph again. This is the current. The curve was like this, no? And afterwards, it's almost constant. Put like this here. So this is for the intensity I, and this is the saturation. Show you have to show where current constant, that is I saturation. So already we give. Now we have to. I'm going to the potential difference that is applied across the cell. Now tell me like how E bar will be. E bar will be towards right. Now the ejected photoelectron in what actual expensive force? Towards left, no? Then still what happened as I keep on increase the potential, so what happened, the amount of current now flowing through the cell will decrease. Any reason we have to give? Because number of photoelectrons striking will decrease. Any reason for that? The maximum kinetic energy electron, if it is able to reach, what will happen to, there will be some electrons open whose kinetic energy will be not sufficient to reach that, because as it starts moving, how electrostatic force will act towards left. Then what will happen? Some electrons happen before reaching collector only. If they come to rest, what will happen? They will trace back, no? And some electrons which are having enough kinetic energy, they'll overcome this electrostatic field, they'll reach collector. So what happened now with zero potential, if there's some 100 electrons were striking, now as you increase the potential reverse direction here, now number of electrons striking will be less than 100. Because those some electrons which are having kinetic energy less than K max, they fail to strike the collector. And what about space charge there? Will be there like that only. Now I'll further keep on increase this potential. What will happen to space charge layer? I think the space charge layer will not get disturbed, no, because how the electrostatic force will act towards left. So the amount of space charge layer will keep on increase, no, and those electrons which are having kinetic energy, so they'll start moving. The electrostatic force will retard. Before reaching collector only, what happen? Some electrons will come to rest and they will return back. So like that, what happens? The number of electrons striking the collector decreases. The current flowing through the wire or the electrons flowing through the wire decreases. Then, so what will happen to this? The current through the emitter will decrease. So this is what happens here. What happened to space charge layer? Will increase. Space charge layer starts diminishing. No space charge layer here. Space charge layer start diminishing. Here what happened? The amount of the electrons in the space charge layer starts increasing. Finally, at this particular point, what will happen here? Zero current. Zero current means none of the electron, none of the photon ejected is able to reach collector. What actually going on there? So we'll call the potential. This is called like a stopping potential. Stopping, the word itself. What is Vs? Vs is called as the potential difference across the tube at which what happen, the electrons are stopped reaching collector. That's why it is called as a stopping potential. So let's write a theoretical one. Space charge layer starts diminishing. No space charged layer here. So what about here? At this particular point, none of ejected photoelectrons or photo none of ejected photoelectrons reach collector. None, I'm using word, or photoelectrons will not reach collector. I'll put like this. Photoelectrons will put like this. This will be proper order. So at this particular point, what about here? Number of photoelectrons reaching collector start decreasing. Here, here what happened? This condition is specifically for this one at stopping potential. I'm writing now nearby that. So finish or no? So no, what actually goes on there? The ejected photoelectron. Look at that spot. The maximum kinetic energy photoelectron itself fails to reach the collector. Means here, let's talk about maximum kinetic energy photoelectron. Photon will come, will interact with this metal, will interact with free electron in the metal, and that particular free electron which interacts with photon will emerge, will get ejected by maximum kinetic energy at stopping potential. So what happened to this maximum kinetic energy photoelectron? It will undergo retardation just before reaching collector. It will go back. So shall we say no photoelectric effect? No, photoelectric effect is going on, but the electric field will not permit the maximum kinetic energy photoelectron to reach collector. You see, if the maximum kinetic energy electron fails to reach collector, what about this electron? Red color electron, this one, which is having kinetic energy less than Kmax, I think it will move somewhere here like this, then come back. So different, all electrons will not have same distance covered. Maximum kinetic electron what happen will go like this. Just before reaching, will return back. So I'll show it here. It'll go like this. Just before reaching collector, it will return back. What about this? It will be like this. Next, other some electrons will be like this. What about zero kinetic energy electron? Since kinetic energy is zero, it will not at all move, no, because the electrostatic force will act towards left. So this is what happens here. That is called like a stopping potential. So at stopping potential open, the electron will just retrace path. Means it will be like this. The maximum kinetic energy electron only itself fails to reach collector. Ejected photon will not reach collector. So shall I say like a K max Kmax ejected photoelectron. I think this will be more. Kmax ejected photoelectron, or photoelectron ejected with maximum kinetic energy itself will not reach collector. What about other things? Definitely they'll not reach. So now no current flows. That's called like a stopping potential. Now let's come for this. What is Kmax we used to write? Kmax, what is the expression for Kmax? Sc by lambda minus work function. So what should be this Kmax here now? At this particular point, should be equal to E into Vs. I'll substitute here. This will become EVS SC by lambda minus work function, or stopping potential equal to SC lambda E minus this one. SC lambda E, and this called like a, what you can call this is the work function here. How to calculate threshold wavelength, where Kmax will be zero, no? That's called like a, the wavelength at which what will happen, the photoelectric effect occurs here. So shall we put lambda less than lambda naught, greater than lambda naught, or lambda less than equal to lambda naught? One small thing, lambda less than or equal to lambda naught. Photoelectric effect occurs. Lambda greater than lambda naught. No photoelectric effect. We should not put lambda greater than equal to lambda naught. How to calculate this threshold wavelength? I think that should be equal to work function, no? Am I right? Sc by lambda naught should be equal to work function. So separately, if you want it, you can write it here. Sc by lambda naught should be equal to work function. So if you want to replace work function, you can replace. And what is lambda naught? Threshold wavelength it is. We are not discussing about the threshold wavelength here. Now we are bothered about the stopping potential. Some books, they are expressed in terms of lambda naught. Instead of work function, they brought threshold wavelength. Yes, you can write in terms of that also. So then the equation will become this same equation. We can also write Sc by lambda, Sc by lambda naught. Okay, so either of this equation, Hc lambda E. I'll make correction. It should be work function by E, that one. Okay, like this here, we can express, we can bring in terms of threshold wavelength also. Okay, let's come for this. What will happen if I increase intensity? I'll keep lambda constant. Let me just vary the intensity. What will happen to stopping potential? We'll see. If I vary intensity, what will happen to stopping potential? If you vary intensity of source, let me show the total graph. Yeah. If I vary the intensity of source, what will happen? Number of photons will increase. If number of photons increases, number of photoelectrons ejected will increase. If number of photoelectrons ejected increases, then current will increase. So what should happen to the current? Current must increase. So how the curve should be now? The curve should be like this. What will happen to stopping potential? The stopping potential is independent of, stopping potential depends on what? Come for it. Kmax. Kmax depends on what? Lambda. And lambda depends on what? Lambda is nothing but energy of photon, no? And we know that if you increase intensity, what will happen to energy of photon? I already covered background yesterday. Rather than fighting here, yesterday only I made a clear-cut discussion. If you increase intensity, number of photons increases, energy of photon constant. Agree? If you increase frequency, energy of photon increases, intensity of source is constant. This is the basic idea. So number of photons per second is nothing but the intensity. So therefore, if I increase intensity, what will happen to energy of photon will not change. The energy of photon will determine Kmax. And the Kmax will determine stopping potential. So therefore, it's quite clear, no? The stopping potential is independent of intensity. So how the graph will be now? So if I plot the graph, the curve should be for different intensities, I'm trying to plot the curve here. So first a red color one. No. Now you can ask questions of why the curves at the increased intensity, stopping potential is will not change here. So stopping potential is fixed here. This is intensity I, 2I, 3I. Why stopping potential should not change? That's what the explanation what we are giving here. As you increase intensity, number of photons will increase, energy of photon will remain same. Energy of photon will determine K max, and the stopping potential depends on K max. And this is write it big. Try to see this. So here is what the total concept is lying for. This it's the equations are in order like this. Huh? Okay, no. Try to check it. So is it graph justified? Okay, next question comes like, what about the with zero potential? Means when potential is zero, you are selected. No potential is applied. No. Then, as intensity increases, we know that as intensity, number of photons increases, and the number of photons, photoelectrons ejected also should increase. Though this cell is not there, so definitely this current what happened should be increasing that one. What about saturation current? Why should increase? Why not saturation current be same? Why not saturation current be same? Saturation current depends on what? Okay, come for this. We have here. That's why I wrote here. So saturation current, shall I say, depends upon number of photons emitted by source per current. Say number of source, number of photons emitted by source per second depends on power, and the power of a source what happen will determine the intensity. Here power means you better think like this. How do I can increase intensity? Not by increasing PS. I'm just going to move like this. The number of photons striking this will increase. Rest mass, see, like please, all of you, rest mass of photon is zero in classical mechanics. No need of any discussion, nothing, finish over. Non-zero, if you say you have to go to quantum mechanics, not their syllabus, finish over. You need not to waste time in that aspect. And finish over. That one, rest mass is zero, finish over that one. That's all. A photon rest mass is zero. There's no element of doubt in that one. When it is in motion, you have to take help of quantum mechanics. In classical, we are in classical mechanics. Rest mass means not like photon at rest, photon in motion. Please use some common sense here. Photon at rest, okay, rest mass. No, not like that. Photon in motion only, the rest mass will be the rest mass. It is called as the mass, what we say in classical mechanics called as the rest mass. And it will be, it's zero. That one. Quantum mechanics, I think it will have that one. Not like a photon at rest, it will have rest mass zero. When it is motion, it will have some mass. No, don't use language here. Stick on to the basics. Okay, this is about the intensity, that one. So I think I have generated two curves. This will be. Next again curve. Let me vary the, all of you got this. If I increase intensity, how to vary intensity? Just bring the source nearer. More photons will strike. More photoelectrons ejected. So saturation current also will increase. That's what I mean to say. How to calculate saturation current? I gave this formula. This is for calculation of saturation current. Okay, let's I'll vary the frequency. Let's see what conditions will come. If I vary wavelength, definitely I'll decrease the wavelength. I'll make lambda less than lambda naught. Lambda naught is threshold frequency. I'll further decrease it. Then as I vary the wavelength, as I decrease wavelength further, then energy of photon will increase. Now, what will happen to number of photons are fixed. I'm making things clear. Number of photons emitted by source per second. But sir, you are having the formula. That's what you should ask a teacher. But you brought it. If I vary the lambda, what will happen here? But sir, okay, you do one thing. All of you, I'm trying to uh, make things very clear because most of you try to think mathematically. Sir, I'll vary lambda. Then okay, sir, you see here. So here, number of photons emitted by source depends on this one, energy of photon. Now, if I decrease wavelength, then energy of photon will increase. The number of photons should decrease. Is it like that? No, number of photons depends on intensity here. And what is intensity? Intensity is power by area. I think you have to go back to the idea. Don't think mathematically here. So if you vary frequency, number of photons emitted by source will not change. But sir, you use this. Then how you justify this one? So let's go back. Photon flux. Let's go back to the intensity. What is intensity? Power by area. Okay, clear this. Power by area. So if you vary the lambda, what will happen to power of a source? Power of source, what will happen will not change. Then 4 pi x square will not change. So intensity will not change. Then intensity into area will give the power flowing that one. So number of photons will not change. So this is just only for calculation purpose. So that's why in the yesterday's class I made a clarity. If you vary frequency, number of photons will not change here. Got this? So now what happen if I decrease wavelength, what happen energy of photon will increase. Energy of photon increases, then Kmax will increase. Come for this, if I decrease lambda, Kmax will increase. Then if Kmax increases, then any conditions will arise here. How the graph we can plot it. For a given intensity, for different frequencies, how the curve will be. There's a last part of theoretical discussion which I'm going to wind up now. Kmax, if I vary the frequency, so let's take help of the formulas.